Friends, welcome to the another video on deadlock. In previous lecture, we see that what is deadlock and the four conditions which are responsible for this deadlock situation. The four conditions are mutual exclusion, hold and wait, no preemptive, and circular wait. In previous lecture, we also see that if system is into the deadlock, it means this all four conditions are present into the system. But it doesn't mean that if any of the one condition is present into the system, there is a deadlock. Now let's see how. For example, here there are two processes, process P1 and P2, and both are requires resource R1 and R2 to complete its task. So P1 first of all sends a request to resource R1. At the same time, P2 also sends a request to access resource R1. Both are trying to access the resource R1 and send the request. Now, for example, the request of process P1 is granted and hence resource R1 is allocated to the process P1. Now P2 is wait for resource R1 to release. Now after some time P1 send request to access resource R2 and this time P2 also send request to access resource R2. This time also, resource R2 is allocated to the process P1. It means its permission is granted. So again P2 goes into the wait state. Now P1 get both resource R1 and R2. Hence it can complete its task, and after completing its task, it can release R1 and R2 both. And then P2 get both resources R1 and R2 and completes its task. So in this example, mutual exclusion is present into the system, but it doesn't mean that there is a deadlock. And we also see that there is no deadlock in this example. Same thing is into the hold and wait. Now let's see how hold and wait conditions is present into the system, but still there is a no deadlock. For example, these traffic are not present into the system. So now what happened? This traffic is waiting for this traffic to move forward. This traffic are waiting for this traffic to move forward. Hence, here is a waiting condition as well as holding condition is present. Here also waiting condition and holding condition is present. So here in this system, hold and wait condition is present into these both junctions. But it doesn't mean there is a deadlock because here is no traffic. It means this traffic can move forward. After completion of this traffic can move forward, and after completion of this traffic, they all can move forward, and there is no deadlock in this example. Now let's talk about the non-preemptivity. For example, in this system, there are three processes, process P1, P2 and P3, and three resources R1, R2 and R3. Suppose process P1 wants to access resource R2, process P2 wants to access resource R3, and process P3 wants to access resource R1. Now in this system, all process P1, P2 and P3 are supposed non-preemptive, but all are trying to access the different resources, and hence this system never goes into the deadlock. The last condition was circular wait, and to understand the circular wait we need to understand two new basic things. Okay, so let's go for it. To prevent the system by goes into the deadlock, or to detect that whether the system is into the deadlock or not, there are several algorithms are available, but the problem is the time complexity and the space complexity of the algorithms. Time complexity and space complexity of that algorithms are much higher. So what we need is some simple solution which requires less time complexity as well as space complexity. So the solution was a graphical method. We have two graphical methods. resource allocation graph, and wait for graph. Okay, so let's understand resource allocation graph. For the detection and prevention of the deadlock into the system, we need to store some information, right? For example, how many processes are there, how many resources are there, which processes are requesting for the resources, which resources are allocated to the process. So resource allocation graph is nothing but the storing this information graphically. Okay, so let's understand. In this resource allocation graph, processes are indicated using circle. Square is used to indicate the resources, and the dot represent the number of instances. For example, here this three circle represent that there are three processes into the system. Square bracket, this square represent that there are three resources, and this dot represent that resource R1 and R2 having one instances, and resource R3 having two instances. Okay, so now let's see how to draw this resource allocation graph. So, suppose process P1 wants to access resource R2. So for that we draw a line towards the resource. This line indicates, this arrow indicates that process P1 wants to access resource R1. Suppose this resource R1 is allocated to process P2. For that we draw an arrow towards the process. This arrow indicates that resource R1 is allocated to process P2. Suppose process P2 wants to access resource R2, so we draw an arrow towards the resource, and suppose resource R2 is allocated to process P3. So we draw an arrow towards the process P3. Now suppose one instance of resource R3 is allocated to process P1. So for that we draw a line towards process P1, and one instance of resource R3 is allocated to process P2. Now to detect that whether this system is into the deadlock or not, we simply need to find out the cycle, that whether there is any cycle in this system in this graphical method or not. Here there is no cycle, it means this system is not into the deadlock. But suppose process P3 needs to access resource R3, then it will send a request for resource R3, and if this happens, there is a cycle, and hence this system goes into the deadlock. So this is something known as resource allocation graph. Let's take one another example. There are four processes in this example: A, B, C, D, and two resources 1 and 2. Both resource having two instances. Suppose one instance of process A is allocated, one instance of resource 1 is allocated to process B, and one instance of resource 1 is allocated to process C. One instance of resource 2 is allocated to process A, and one instance of resource 2 is allocated to process D. So now process resource 1 and 2 not having any free instances. So now suppose A send a request to access resource 2, it will wait. Same thing, suppose C wants to access resource 2, it will also wait. And because of this, there is a cycle in this graphical method. A to 1, 1 to C, C to 2, and 2 to A. But this system not goes into the deadlock. Why? Because process B and D already have the resources, already have their enough resources, so they both can complete their task, and after completion of their task they will release the resource. So process B and D will release the one instance of resource 1 and 2. Now one instance of resource 1 and 2 are free, so this instance is allocated to process A and C, and A and C also complete their task. So in this example there is a cycle, but it doesn't mean that it goes into the deadlock. So if there is a cycle into the resource allocation graph, system may leads to the deadlock but never ensure about the deadlock. But if there is always one instance of resource, then if there is a cycle, it means there is a deadlock. So I think it's enough for today's lecture. We will learn wait for graph in the next lecture. Till then, if you have any question or doubts, you can message me on vishaltank.quora.com. You can mail me also, and you can contact me on WhatsApp also. Okay, so that's it. Bye bye, and don't forget to subscribe.